A very warm welcome to the session on evaluating hypothesis, probability learning, approximately correct hypothesis, and function approximation in data-driven artificial intelligence system. So, coming to the topic, what is hypothesis and how is it important in machine learning? That's what we are going to learn in this particular session. Talking about hypothesis, hypothesis is an assumption made on a particular evident facts. So it is an assumption that might be true and or false, but you have to test it in order to approve a hypothesis then. Example, if you claim that UV light may damage eyes and potentially cause blindness, in such case you may assume that UV rays are harmful to the eyes and may cause blindness. So what is the use of hypothesis in machine learning? In machine learning, hypothesis is used in supervised learning. Hypothesis model, the hypothesis that you are going to work with in machine learning models learns a function to map inputs to outputs using available data. Hypothesis testing is a fundamental concept in statistics within the machine learning. As I said, in machine learning, we are going to use hypothesis in supervised learning. So the supervised learning objective is to determine the best hypothesis from the hypothesis space to map inputs to correct outputs. So now what is hypothesis space? The set of all hypotheses or assumptions that you have made based on the particular content is called a hypothesis space. So the set of all possible legal hypotheses or the hypothesis set is called as your hypothesis space. So it is used in supervised machine learning algorithms so that you will be able to find out the best hypothesis of all the set of hypotheses that are present so that you can map input to the output. It is influenced by problem framing, model choice and configuration then. So we have talked about hypothesis space where we have talked about all the set of hypotheses present there. So what is a hypothesis? As I already said, hypothesis is an approximating function that describes the target in supervised machine learning. So we need data bias and data restrictions as determinants to work out on the hypothesis, and the purpose is to map the input to the output based on the evaluation and prediction. Based on the facts that you have given as an input, you get certain outputs. So it is used for evaluation and prediction there. And the equation for the hypothesis is y is equal to mx plus b, where y is the output or prediction, x input or feature, m slope representing the relationship, b intercept indicating the starting point there. So this is an example that you can see here. In this example, you can see that a set of hypotheses are being given to you. That is two-dimensional coordinate plane showing the distribution of the data is given over here. So we assume that some test data by which the ML algorithm predicts the output for the input as follows is being given there. So out of this, we have to find certain assumptions are being made on this particular data. So if we divide this coordinate plane in such a way that it can help you to predict the output or the result. So when you divide it, this is how your data looks like. So based on the test data, the output will result as follows here. However, it's not the only way that you will be able to divide the data, or it's not the only assumption that you can make. So for one assumption, this is how the data might be divided. For other assumption, this is how the data might be divided into. So as we already talked about hypothesis space, it is a set of multiple hypotheses there. It is a set of hypotheses there. So as you're having multiple hypotheses, this is how your hypothesis space looks like. For each individual, best possible way is called as hypothesis. Hence, hypothesis and hypothesis space would look like this. There are two important types of hypothesis, that is null hypothesis and alternative hypothesis. So when we come to the null hypothesis, it states that there is no statistically significant effect in a set of observation. That means once some assumption is made, the assumption is not making any difference to the observation. That means it is almost accurate. In such case, it is called as a null hypothesis. It is used in quantitative analysis, including finance and market research, to test the validity of the ideas. So there is no effect on your data there. Null hypothesis will be represented as H naught. whereas alternative hypothesis is represented as H1 here. Okay, so when we are talking about H1, now what is alternative hypothesis? An hypothesis that contradicts the null hypothesis is called as a alternative hypothesis. So direct contradiction of the null hypothesis is called as your alternative hypothesis. If one is true, the other must be false there. So it is used to indicate a significant effect in a set of observations. So it has some effect on your data. Because one of the assumption was proved wrong, this assumption might be proved right. So there is some effect on the data. Okay, alternative hypothesis is represented by H1 there. So null and alternative hypothesis work together to test the ideas. When you're checking with your hypothesis, we have to be sure that it's giving you the accurate results. So significance level is something that plays a vital role here, so that you can say how accurate is your hypothesis that you are judging with. So defined on an experiment and determinant, tolerance for error and level of significance is being given here. So commonly the significance level will be set to 95%. That means 5% chance of error is what we are expecting. So significance, by looking at the significance level, we can also set the critical value there. So if the significance level is 98%, then the critical value will be 0.02% there. Checking with your p-value over here, the p-value represents the strength of evidence against a null hypothesis in the statistics. So how well is your hypothesis true is what you have to check with. So p-value represents the strength of evidence against null hypothesis in statistics. It's a probability that the random chance produced the data or something rarer under the null hypothesis condition there. If the p-value is smaller, smaller, then we say that the stronger evidence against the null hypothesis. And if p-value is larger, weak evidence against the null hypothesis. That means smaller the p-value, you are indicating the significance as high. That means it is accepted. Your hypothesis is accepted there. The larger the p-value, then you're against the null hypothesis. That means you're rejecting your null hypothesis. You're going for the alternative hypothesis then. So p-value always in decimal, it is 0.035. And it depends totally on your critical value. So if p-value is less than the critical value, null hypothesis is rejected. And if p-value is greater than your critical value, your null hypothesis is accepted then. So we have talked about what is hypothesis, what is its use in machine learning with supervised learning. Then we have talked about types of hypothesis. But the one thing that we have to talk about is evaluating the hypothesis. So when you check with evaluating the hypothesis, in here we talk about how best the hypothesis or the assumption that you have come up with is accurate. To what extent is it accurate? So you have to evaluate your hypothesis to judge the accuracy of the hypothesis. So hypothesis formulation, formulate a hypothesis for a given training data set. So given a data set, you will be dividing the data set into your training data set and test data set. So if you're checking with your training data set, now you are formulating a hypothesis on the given training data set. So hypothesis for example, if you're checking with a particular example, for enjoy sport, you will be predicting if a person can enjoy their favorite sport based on the attributes. You are going to, for example, if you are checking with a particular data set of sports as such, in the sports you have to decide whether a person enjoys the sport or not, right? So in order to decide, first you check with the attributes. Based on that, you come to a particular conclusion and you are going to predict it. So hypothesis for enjoy sport, predicting if a person can enjoy their favorite sport based on the attributes, is a good example that you can work with. So when you are evaluating the hypothesis, there are 3 questions that we need to answer. Okay, so that you will be able to assess the accuracy of the hypothesis using the statistical measures. So the 3 points that you have to focus on are generalization, comparing hypothesis, and data efficiency. So if you're checking with generalization as such, when we are talking about a generalization, you might have come to the conclusion, or you have come to a conclusion, or you have drawn a hypothesis based on some sample facts. Of course, your hypothesis is working good with the sample facts. What if an additional data is added to it? Then, will your hypothesis also satisfy the additional requirements that are being additional data which is being added? That's one point that we have to answer. Okay. And next, comparing hypothesis. Comparing hypothesis is how likely that the theory outperforms another across a broader data set, indicating high accuracy. That means you're having two hypotheses, H1 and H2. You have come to the conclusion that H2 is accurate, but will H2 also suit to the other data when added new? So whether sometimes H2 might work good, sometimes it might not work good. So how accurately will your H2 work good when another data is added outside your boundaries there? Then data efficiency. What's the best strategy to use limited data for both learning and evaluating the hypothesis accuracy? So you're having different strategies. So which is the best strategy that can be applied is what you're going to talk about in your data efficiency. These are the three questions that we have to answer while you're going for evaluating the hypothesis. That means you cannot blindly come to a conclusion. You have to check all these conditions in order to approve a particular assumption that is being made as an hypothesis there. So evaluation of hypothesis is crucial to building robust machine learning models and making accurate predictions there. So when you're going for a model adoption of the best thing, the main thing that we always concentrate is high accuracy. So this is something very important. How accurately are you going to work on your hypothesis that is being given to you? So how accurately do we work? It's all based on two challenges there. Bayesian estimation and estimation variability. So for example, an example has been given to you here. Accuracy is vital in medical treatment models. So you can't just pick some data and make some assumptions and come to a conclusion that it is working fine. You have to be very accurate while you're working with your medical treatment data. So for such things, you have to come up with future accuracy, right? So in order to work out with your future data, so accuracy is very much important. So there are two challenges that we come across here, that is Bayesian estimation and estimation variability. So what is Bayesian estimation? It's the initial accuracy over training instance, is a poor predictor or future accuracy due to bias. So what happens in bias estimation? It's an estimation that you have made over your training instances, but is a poor predictor of future accuracy because there is some error present within your initial data that you have chosen. And then estimation variability. This may differ from the true accuracy even when unbiased test instances are present there. So you're talking about two things over here. You're talking about true error and sample error. So what is true error and what is sample error? So when you work with your true error and sample error, so we distinguish between two concepts of accuracy. To put it another way, one is the hypothesis error rate based on the available data sample, and the hypothesis error over the complete unknown distribution D of examples is the other. That means true error is going in the true error, what we are going to check out is how well your data is working good on the entire data, and how well is your data good with the sample of data that you have taken. Okay, for example, let me tell you the other way. There are set of students, 60 students are there. So 60 students, out of 60 students, you have just took the data of 30 students. You have randomly decided that 30 students are girl students, or girl students as such. In such case, you have just took a sample of the data. Instead of 60, you have took only 30, right? So for that particular sample of data, how well you are able to give the accuracy of the accuracy over there with your target function. Okay, so you are having your constants here, you are having some subsets of the data that are being taken, and you are also having your target function. So that means you are in what is a target function here? Target function is the prediction that you have made that this is the output that you want. So you have to compare the you will be comparing your sample of data's output with your target function. If both are equal, then it means it is high accuracy. If there is a mismatch, then there is some deviation present there. So coming to your sample error. Sample error, it is denoted by error H of hypothesis, okay, with respect to target function F and data sample S. So what is a target function? Target function is the output that you are expecting. And so for that particular thing, you are going to check with your data. For a particular sample of data, you have estimated over here. So 1 by n, n means the total number of instances that are present within your data, or number of examples that are present within your data. So where n is the number of examples. Okay, so you are having delta f of x comma h of x is 1 if f of x not equal to h of x, otherwise 0, right? So what do you mean by that? If f of x not equal to h of x, then your sample, whatever you have considered, is having some error. If f of x is equal to h of x, then your target function and your assumption, whatever you have made, are both same. That means you have got a high accuracy rate there. So that is called as a sample error. Sample error means you have calculated on the sample of the data that you have taken from your data set. And talking about the true error is calculated on the entire data. Based on a particular distribution, you are going to calculate the true error there. So problem estimating error, you are having bias and variance that we have talked already. So if S is a training set, the sample that you have taken, that is error S of H, is optimistically biased. So you are talking about bias is equal to error of a particular sample minus your true error. This is your sample error minus true error that you can check with. So variance, even when with unbiased S, error S of H may still vary through the entire distribution. Okay, so if you check with the hypothesis as over here, you are having 40 examples, out of which you might have misclassified 12 examples. That is the sample that you have talking about. So if there are 12 misclassified, then 12 by 40 is equal to 0.30. That's the error present. So talking about probability learning approximately correct hypothesis. So probability learning approximately correct hypothesis is the assumption, how accurately are you able to predict, right? So the probability of learning approximately correct hypothesis is what you're going to check with. So when you're working with a particular training set, you have to generate some hypothesis on it. So, and you have to check how well these hypotheses are suiting or are judgeable over here. Okay, for that we are going to work with your computational learning theory first. So computational learning theory is a mathematical and theoretical field related to analysis of machine learning, where you will be talking about probability of successful learning, number of training examples, complexity of hypothesis space, accuracy to which target function is approximated. So the checking with this particular thing, we are going to check with how the data is being estimated then. So you can check that X, the set of all possible examples or instances, Y, the set of all possible labels or target values. So for introductory purpose, we are assuming that Y is equal to -1 plus 1, that is your binary classification. So we are going to take C is a subset that we are talking about, the concepts actually. Okay, C is a concept, that there are a number of concepts within your class. So a part of the concept is the small c that we are checking with. So if Y is equal to -1, 1, then we can identify a particular subset, C, as a subset of X over which it takes value 1. So concept class is a set of concepts that are present there. So generally what we do is a trainer will be training a particular machine to check whether they are approximately or accurately judging things or not. So considers a fixed set H of possible concepts, also referred to as hypothesis set or hypothesis space. Out of all the possible concepts, you will be picking some of the concepts, check according to your distribution. If they fix, then we will be going on further. So here we use the label sample S to select a hypothesis, a particular hypothesis out of the hypothesis space that has a small generalization error with respect to the target concept there. So probably approximately correct learning. So when you are checking with your probably approximately correct learning, we specify the small parameters epsilon and delta. So and we require that we the probability at least be 1 minus delta, a system 1 minus delta, that is a system learned concept with the error at most epsilon there. So when you're checking with your epsilon and delta parameters here, epsilon is an upper bound of the error in accuracy with which H approximated there. So accuracy is 1 minus epsilon there, and delta gives you the probability of failure in achieving this accuracy. So it is 1 minus delta, that is the confidence there. So if you are checking with the accuracy of a particular hypothesis there, then it is 1 minus epsilon, that is for your what can we say, that is for the concept that you are working with. If you are working with your entire distribution that gives the probability of failure in achieving high accuracy, then that is the confidence, that is 1 minus delta. So this is how you are working with your probably approximately correct formula. A hypothesis is said to be approximately correct if the error is less than or equal to epsilon. So whatever assumption you are making, it is approximately correct if the error is less than or equal to epsilon there. And the goal is to achieve low generalization error with high probability. Okay, so let's see with an example here. You're having a problem here. So you can see you are having the error rate for a particular sample of 10. Okay, so hypothesis H1 generated the error with respect to the price and engine power for the given 10 samples. You are having 10 samples given for which you have generated the hypothesis, that is H1, okay, with respect to price and engine power then. So you can see that the given is you are having epsilon 0.05 and delta is equal to 0.20 there. Okay, so as we have already seen with the accuracy and confidence then, right? So let's check with this. P of H1 greater than 1 minus delta. Right, now first let us identify what is P of H1. So if you check with this in P of H1, what is the epsilon value here? Epsilon is 0.05. So which values are less than 0, which values are not are greater than 0.05? If you check, 3 is greater than 0.05 and 8 is also greater than 0.05. So you are having two values that are greater than 0.05. That means 8 samples are cooperating and 2 samples are not cooperating them. So P of H1 is equal to, as 8 samples were cooperating, 8 by n, right? N means 10 over here. 8 by 10 is equal to 0.80. Okay, so that's your concept that you have generated with. Now check with the delta there. Okay, so what is the delta value there? So here 1 minus delta. What is delta? 0.20. So 1 minus 0.20 is 0.80. So now check with it. P of H1 is equal to 0.80 and your delta value over here is 0.80. So your P of H1 is greater than or equal to 1 minus delta. Whenever your P of H1 is greater than or equal to 1 minus H1, your H1 is probability approximately correct, because it is equal to, it is satisfying the condition, accuracy is high over here. Just check with another example where you are not having the same values. So you are checking with 0.05, so you are having some, if you check with the error epsilon value here, you are having 3 deviations, 3rd, 4th and 9th position, there seems to be a deviation. So out of 10 samples, you are having 7 samples that are accurate, 7 by 10 is 0.70. So P of H2 greater than or equal to 1 minus delta, that is 0.70 less than 0.80. That means it's not accurate. There is some error present here. That's how you're able to judge. So now you're checking with that of function approximation. So function approximation in machine learning refers to the process of finding an approximate representation of an unknown function based on a given set of input-output pairs. The goal is to learn a model that can generalize from the observed data and make accurate predictions for new unseen inputs. So that's mainly your function approximation. In function approximation, the unknown function is typically represented by a hypothesis or a model, which could be a linear model, a neural network, a decision tree, or any other suitable mathematical representation there. With this, we come to the end of your session with respect to the hypothesis. Thank you.